In a linear relation, there is a relationship between two variables, and depending on the type of linear relation, that relationship can be defined as either being a direct variation or a partial variation. In this video, we will be discussing partial variation. If you haven't already, make sure to watch part 1 on direct variation, and there's a link to that video in the description box below. A partial variation is a relationship between two variables in which one variable is a constant multiple of the other plus a constant number on top of that. So with a direct variation, we said that it was a straight line that was created because of the fact that the data points were increasing or decreasing by the same consistent value or the same consistent constant multiple. So it was either doubling by the same number or it was increasing by 5 or decreasing by 10. But with the partial variation, yes, that is still happening. So maybe your x value is increasing by 2 or increasing by 5, but then on top of that increase, you are going to be adding or subtracting another constant number or value. What is very identifiable about the graph of a partial variation is that it is a straight line that does not pass through the origin. So that was one of the key things that we mentioned about a direct variation. A direct variation did pass through the origin, the point 0, 0. But you can see here on the graph that is on your screen that a partial variation does not start at the origin. In fact, in this example here, this particular graph starts at a value or a y value of 6. It is not starting down here at the origin located at 0, 0. If we wanted to use an equation to represent a partial variation, we could use the template y equals mx plus b. M, as we know, represents the slope or the rate of change. X and Y represent the values of coordinate points or data points that are part of your linear relation, and B represents your initial value. Some other names that we can use for B are things like the y-intercept, or another third name that you might see used to describe B is something called a fixed value. So in a direct variation, we really didn't use this b value because our initial value or our starting value in a direct variation was always 0 because our graph started at the point 0, 0. However, in a partial variation, because the graph doesn't start at a value of 0, 0, and it could start really anywhere other than 0, 0, you're going to find that with partial variation, you will have another value attached at the end of your equation. So in all of the examples that we're going to do today, we are going to have to spend a lot more time focusing and paying attention to what that initial value is. In our first example, we're asked to complete the following chart given that y varies partially with x. So right away in the question, they are telling us that the data that we're going to be dealing with represents a partial variation. So the first thing that we should attempt to do is fill in all of the missing spaces in our data table. So I'm going to suggest that we start with the y column and try to establish or figure out what pattern exists in the data points and if there is a pattern at all. So let's start with the first value that we see here, which is a 6, and then the 6 grows to become a 9. So the pattern that I see there is that, well, in order for me to go from 6 to 9, I know that I can add 3. All right, so we're going to now try to fill in the next value. And we also want to make sure that we're not skipping any numbers along the way. So what do I mean by that? If I take a look at my x column, I see that it started at 0, and then it increased to 1, and then it increases to 2, it increases to 3, it increases to 4. So there is also a nice, steady, consistent pattern in my x values because I can't assume that my y values are going to consistently be skip counting by 3 while my x values are jumping all over the place. I have to be able to apply this +3 pattern to my y values, and I can only do that if my x values are staying consistent as well. So there has to be a consistent change in my x values. So because I see that my x's are nicely increasing by 1 each and every time, I know that my y values will consistently be increasing by 3. So we're going to start at 6, we're going to add 3 to get 9, and then we're going to add 3 again, and that's going to give us 12. We know that this is correct because if we follow the pattern to the next row and add 3, we know that 12 plus 3 is 15. So we're going to repeat the pattern again, and 15 plus 3 is 18. So now if I look at my very last value, it jumps ahead to 27, and that doesn't follow my consistent pattern of adding 3, because I know that 18 plus 3 is not 27, it should really be 21. So to me that means that they've tried to trick us, and they've actually skipped some numbers in between 18 and 27. And now, if you notice, there is also an empty space that we need to fill in our x column. And when students recognize that there is a nice consistent pattern of adding 1 between each of the x values provided, they kind of jump the gun and they say, oh, well, this must be 5, because we're counting 0, 1, 2, 3, 4, 5. But we know that that can't be true, because in our y column, if we follow our pattern of adding 3, 18 plus 3 is not 27. They must have skipped some numbers in between here and jumped ahead to some other data point along the way. So in order to figure out what number is missing here, what I'm simply going to do is just make myself another smaller t-chart on the side, and I'm going to try to figure out what numbers we're missing. So I have an x column, I have a y column. Our last known data point was 4 and 18. And so I'm just going to continue my pattern of adding by 3 in order to generate the remaining values. So my y value, if I do 18 plus 3, should be 21. And then the corresponding x value that goes with that should be 5, because remember, our x values are simply just increasing by 1. So my next data point would be 5 and 21. My next x value would be 6. And then if I continue to add 3 along my y column, my next value would be 24. And I'm going to keep the pattern going. My next x value would be 7. And my next y value, if I add 3, would be 27. Oh, and there it is. 27 in my y column is the value that they ended our table of values with. And I can see from my own charting and calculations that the corresponding x value to go along with 27 should actually really be a 7. So I'm going to fill in a 7 in my x column. So the first question we are asked is, what is the initial value of y? So to find the initial value of y, we need to go to our table of values and we need to look in our x column for the value 0. When we locate the value 0 in our x column, the initial value is going to be the y value that is attached to it. So when my x is 0, my y value that corresponds to that is a 6. So my initial value of y is going to be 6. Now remember, there is a very specific letter that we use in math to represent the initial value. We use the lowercase letter b. So when we are stating the initial value, we're going to say b equals 6. Students sometimes make the mistake of thinking that the initial value of y is automatically just the very first y value that you see in your table of values. And sometimes, or most of the time, yes, that is true, but you need to be wary because not every table of values is going to start with an x value of 0. Sometimes they try to be tricky and they will skip over a 0 and they'll start the table instead at 1. And so then students will think, oh, if my table starts at 1, the matching y value to that would be 9, and so my initial value is 9. But that is not the case. When you are looking for your initial value in a table of values, you need to look for your x value of 0. The next question is, what is the slope or the m value? So back in our lesson or video on slope, one of the ways that we talked about how to calculate slope was from a table of values. And the formula that you can use from a table of values is m is equal to delta y divided by delta x. So that is the change in your y column divided by the change in your x column. So we have that already listed out for us. And if I go back to my table and take a look, the change in my y column was 3. Each of my y values was increasing or growing by 3 consistently each and every time. So my delta y is going to be 3. My delta x, or the change in x, is going to simply just be 1 because all of my x values are increasing or growing consistently by 1. It doesn't matter that they skip some numbers here between 4 and 7 because we were still able to kind of go off to the side and continue the pattern by increasing our x values or x column by 1. So I'm going to go back down here and I'm going to input those values into my slope formula. So my delta y was 3, my delta x is 1, 3 divided by 1 is 3. So my m value is going to be 3. Now that I know my b value and my m value, I can then move on to part C, which asks us to write an equation that relates y and x in the form y equals mx plus b. That's just a fancy way of saying take your m value and your b value and stick them into the correct place in that equation template, y equals mx plus b. So remember, that is going to be your template for all linear relations. So we're going to keep y exactly the same. We're not going to touch that. In the place of m, I'm going to insert my slope, which we calculated to be 3. We're not going to touch the letter x, and we are going to put in a plus sign, and then my b value is 6. That was my initial value. So the equation for this particular linear relation is represented by y equals 3x plus 6. So really what that's telling us is that we take our x value, and that could be any x value, we multiply it by 3, we get an answer. To that answer, we're going to add 6, and that should be able to generate a y value. So let's just do it really quickly and kind of come back up here and see that it actually makes sense. So let's see, 3 multiplied by an x value of 0 is 0. 0 plus 6 is 6, so that works. 3 times an x value of 1 is 3. 3 plus 6 is 9. 3 times 2 is 6. 6 plus 6 is 12. So this equation truly does represent this particular data set. Example number 2, MPJ is planning an awards banquet. The cost of renting the banquet facility and hiring serving staff for the event is $675. There is an additional cost of $12 per person for the meal. So the first thing we need to identify is the fixed cost. Now, fixed cost is just another way of asking you to identify the initial value or your B value. So the fixed cost is going to be the $675. That is a price that is not going to change. So just to rent the banquet facility and hire the staff, it's going to cost you $675, even if no one ends up showing up to this party or this event. You still need to pay the money to rent the facility for the event and hire the serving staff, and they need to be paid regardless of if anyone shows up to the party or not. So our fixed cost, or B, is going to be Let me just change that pen. $675. All right, part B, identify the variable cost. Now, variable cost is just another way of asking you to identify the rate of change or the slope, which is represented by our lowercase letter m. So in this situation, the variable cost is the price that is going to change, or the total price that is going to change. So it's $12 per person for the meal. Now, I don't know how many meals I need to buy because I'm not sure how many people are going to come. If only one person shows up, well then it's just $12 for that one person. But if 6 people show up, well then that price is going to change because 6 people, $12 per person, that's a total cost of $72 just for those people. So that is a variable cost. It can adjust or change depending on the number of people. Another way, if you're not completely sure, to identify this variable cost is you can look for a keyword, and that keyword in the problem is going to be the word per. So that word per usually is the signifier or the identifier for the variable cost. So we're going to go ahead and write that in. We're going to say m is equal to 12. So now that we know those values, we can go ahead and write an equation to represent the relationship described in this question. Now, I'm going to be a little bit fancy. I don't want to use the letters X and Y just because this is a very specific question and there is an actual situation that's happening here. So I'm going to say for my variables, let C represent the total cost for this beautiful awards banquet. And I'm going to say let P represent the number of people. So it's the number of people that are attending this awards banquet. So M and B, I already know, so I'm good to take those values and just insert them into my equation template of y equals mx plus b. The only thing here now is the y and the x. Because I've chosen not to use y and x, I'm going to use c and p. So I just need to think about this logically and think about which variable would be plotted on which axes. So cost and people, or number of people, are the variables that I'm working with. So the total cost, C, is going to depend on the number of people that actually come to this party. The cost for 2 people is going to be much different than the total cost for 100 people. So C is going to be my dependent variable, and dependent variables are always plotted on the y-axis. So what I'm going to do here, just to show you, is I'm going to write the original template for a linear relation, y equals mx plus b. So instead of the letter y, I'm going to use a capital C for cost. Cost would be plotted on the y-axis. Then we have an equal sign, and then we need to put in our m value. Our m value is 12 because it's $12 per person. And so that works out perfectly because on the x-axis is where I would plot number of people. And that makes sense because it is $12 per person, and P represents people or number of people. And then I have a positive sign, and my B value is 675. So the equation for this awards banquet would be C equals 12P plus 675. So now in part D, we're asked to use that equation to determine the total cost if 500 people attend the banquet. So 500 people means that in the place of P, I'm going to substitute the value 500, and I'm going to solve for the total cost. So I'm going to start with 12 multiplied by 500, which is going to give me 6,000, plus 675 is going to give me 6,675. So I'm just going to write a sentence. Therefore, the total cost would be $675. Don't forget to put in a dollar sign as your unit. The best way, I think, to understand the true differences between direct and partial variations is to work through a problem that combines or compares both of them together at the same time. So here we have a problem that says the Tesla Electrical Company charges $25 per hour to do electrical work, plus a fee of $50 for the estimate on the proposed work. The AC/DC Electrical Company charges $50 per hour. So the first thing we need to do is write equations to model each relationship for each of the different companies. And they've picked letters for us. They want us to use C to represent the total cost for any work done, and let lowercase h represent the number of hours worked. So we're going to just take apart all of the information given to us in the question, and we're going to translate that into equations. So let's start with the Tesla Electrical Company. So we know that our equation is going to start with a capital C for cost or total cost. So the Tesla Electrical Company charges $25 an hour. So we were asked to use the letter H to represent hours. So I'm going to put into my equation 25H. So that represents $25 per hour for every hour. But then on top of that, they are charging you $50 just for an estimate for the amount of work that you are asking them to do. So the equation then for the Tesla company would be C equals 25H plus 50. Now on the other side, we have the AC/DC Electrical Company. And for these guys, they're just going to charge you $50 per hour. That's it. So yeah, a little bit more expensive for every hour of work that they need to come and do, but that's it. There's no extra charge on top of that. So now that we have our equations, we can go ahead and create tables of values to organize the data for 0 to 4 hours of work. So they only want to see data points or numbers ranging from 0 to 4 hours of work. We don't have to go beyond that. So I'm going to go ahead and just set up my tables, and then we'll talk about how to fill them in. All right, so here are my tables of value that I've set up. So I have one column set up for time, and time is measured in hours or units of hours, and I just filled in hours 0 to 4. And then I have a separate column for my cost, and my cost is going to be measured in dollars, so I put a dollar sign symbol. Did the exact same thing for the AC/DC Electrical Company. So we're going to use the equations now to calculate the corresponding costs. So starting with the Tesla Electrical Company, the equation was 25H plus 50. So we're just going to take 25. In the place of H, we're going to insert the amount of time that we're talking about, and our table is starting at 0 hours. And then on top of that, we have that $50 cost for the estimate. So 20 multiplied by 0 is 0. 0 plus 50 is 50. And we're going to continue this pattern all the way down our table. We've got 25 times 2 plus 50, 25 times 3 plus 50, and 25 times 4 plus 50. So if we calculate all of these values and fill them in, the next one would be $75, $100, $125, and $150. We're going to do the exact same thing for the AC/DC Electrical Company, but we're just going to make sure that we use the equation that we developed for this particular company. And the equation for this company was 50 times H, or 50H. So we have 50 multiplied by the number of hours. So we can just do 50 times 0, 50 times 1, 50 times 2, 50 times 3, and 50 times 4. So nice and simple. And we go ahead and fill those in, and we'd get 0, 50, 100, 150, and 200. So our follow-up question, now that we have our tables of values ready to go, is which relation is a direct variation, and how do you know? So remember, way back when we talked about direct variation, we know that a direct variation is one that begins or starts at the point 0, 0. So we are going to go to our tables of values, and we're just going to look for the table that has the data point 0, 0. Well, if I look at my Tesla company, when the time is 0, the cost is $50. But for the AC/DC electrical company, when the time is 0, the cost is also 0. So they don't charge you any money for doing any or 0 hours of work. So the AC/DC electrical company is the relation that is a direct variation. Okay, so if you wanted to fill that in, you could state AC/DC represents a direct variation because it starts at the point 0, 0. So now we want to go ahead and graph those data points for both companies on the same Cartesian coordinate grid. And the reason why we want to graph both of them on the same grid is so that we can do some comparing and analyzing about when each company would be the better choice. So again, make sure that you are going to go ahead and label your axes appropriately. So we have time in hours and cost in dollars. Remember, time is always plotted along the x-axis. So time in hours is going to go down here on the bottom of our grid. And along the side on the y-axis, we're going to have cost in dollars. We are going to also include a title for our grid or our graph. And remember, your title should always be whatever variable is plotted on your x-axis versus whatever variable is plotted on your y-axis. All right, so if you make your graph, it should look something like what you're seeing on the screen. So I made sure to use 2 different colors so that I would be able to tell the difference between each of the companies, and then I also went ahead and labeled my lines. So my blue line represented data points for the Tesla company, and my red line represents data points for the AC/DC company. Pay attention to also how I labeled my axes. So because we put time on the x-axis and we used the letter H to represent time in hours, I also included the little letter H. And for cost, I included the letter C since that was the variable that we used for total cost. All right. Now, either from looking at our graph or going back to look at our table of values, we want to figure out which company should we use for 3 hours of electrical work. So if we needed to hire somebody for 3 hours of work, who would we want to choose? So since we have the graph in front of us, let's go ahead and look at our graph. So I'm going to zoom in a little bit here. And we're going to look for time, and we're looking for a time of 3 hours in particular. So if I go to the 3-hour mark and just kind of look up, for the Tesla company, at 3 hours, they are going to charge you $125. But for 3 hours of work, the AC/DC company is going to charge you $150. So obviously, you always want to go with the company that's going to charge you less money. So the better choice, if I need to hire somebody for 3 hours of work, would be the Tesla electrical company. So although we are going to go with the Tesla company for 3 hours of electrical work, we're also asked, does this company always offer the best deal? So let's go back to our graph and do a little bit of a comparison. So what happens if I want to go above 3 hours of work? What if I need somebody for 4 hours of work? Well, if I look at my graph at 4 hours, the Tesla company is going to charge me $150, but the AC/DC company is going to charge me $200. So at 3 hours or above, the Tesla company seems like the better choice. They have cheaper prices. And if we were to even just compare the steepness of these lines, the AC/DC line is much more steeper or slanted than the Tesla line, which signifies that it is the more expensive company. So at 3 hours, 4 hours, 5 hours, and so on, Tesla is always going to be cheaper than the AC/DC company. But what if I don't need 3 hours or more than that? What if I need less than 3 hours? So let's see what happens lower than that. So at the 2-hour mark, well, surprise, surprise, both companies will actually charge you $100. So at the 2-hour mark, it doesn't really matter who you choose to go with. They're going to charge you $100. But what if I want less than that? What if I only want 1 hour of work? Well, at the 1-hour mark, AC/DC is going to charge me $50, but at the 1-hour mark, Tesla is going to charge me $75. So Tesla is not always the best choice, because if we're going under 2 hours, Tesla becomes the more expensive option and AC/DC becomes the better choice. What if I don't actually end up hiring somebody? If I say, I'm going to figure it out myself and just fix it myself, well, for 0 hours of work, AC/DC isn't going to charge you any money. But even for 0 hours of work, you still have to pay the Tesla company $50, because remember, that $50, that fixed cost of $50 is the cost for just the estimate. So for having someone to come over and look at your work and to figure out what the problem is, they're still going to charge you $50. So Tesla is not always the best option. So there's a couple of different scenarios then that we can identify. If you need more than 3 hours of work done, the better choice of company would be Tesla. They tend to be cheaper if you go above and beyond 3 hours or more. But if you need less than 2 hours of work, well then AC/DC becomes the better choice. They are much more cheaper than Tesla. If, however, you need exactly 2 hours of work, remember, both companies charge the exact same price of $100. So really, it's your preference which company you choose, and it doesn't matter because they're both going to charge you $100. So you could choose either company at the 2-hour mark. Our last question is, what is the difference between the two relations? So if we had to come up with some concrete differences between the two, what could we say? Well, for the Tesla company, if I go back and look at my graph, so my Tesla is represented by the blue line, the Tesla is represented by a partial variation. My graph does not start at the origin, it starts at 50. It has an initial value of 50. So Tesla is represented by a partial variation. AC/DC, on the other hand, the line goes through or touches or crosses the origin. It goes through 0, 0, and it has an initial value of 0. So AC/DC is actually representing a direct variation. So I've written that information down, and I've stated that Tesla is a partial variation where the graph starts at the data point 0, 50, and AC/DC represents a direct variation, and the graph starts at the data point 0, 0. So let's put it all together and just summarize everything that we've learned between part 1 of our variation video tutorial and this video, part 2, focusing on partial variation. So we're going to focus on 3 different types of data: table, graph, and equation. So let's start with a direct variation. So if we were looking at a table of values and you wanted to tell if it was representative of a direct variation, you need to see 0, 0 as your initial value. So for example, if I were to fill in this table of values here, here's my X column, here's my Y column, I need to see that 0, 0 is my starting point, and it doesn't matter what these points are, so it could look something like this, where 0, 0 is the clear starting value for my table of values. If I was looking at a graph, Well, then to tell if it was a direct variation, remember that your graph has to pass through the origin. And the origin is that data point 0, 0. So your graph needs to have this point here at the origin, and it needs to either increase from there, or you might have a graph that is sloping downwards. So it still can go through the origin, but maybe instead it is, going downwards. And if you are looking at an equation, remember that for a direct variation, the equation takes on the form y equals mx. There is no b value here on the outside because remember b represents the initial value and your initial value is a 0. So no point in including that in the equation. So the only thing left for you to work with in the template is y equals mx. So really your equation can take on a couple of different forms. It could look like y equals 2x. You could have a decimal, y equals 0.5x. You could have a fraction, y equals 2 over 3x. It could be a negative value, so maybe something like y equals negative 5x. All of these are examples of equations that represent a direct variation. If we were talking about a partial variation and we were focusing on a table of values, you would be looking for something that has an initial value other than 0. So it could be any number, any value, it would not be 0. So if we had to come up with our own table as an example, you might see something that looks like this. The starting x value is 0, but the initial value of y that corresponds to that might be something completely different. And then you could fill in the rest with anything else. But really the key factor here is that your initial value of y when x is 0, it is not going to be 0. Now sometimes they might trick you. I'm going to erase this all. And they'll try to trick you and they'll skew the table a little bit. So normally we're looking for 0, 0 to show up at the very top or in the top row of your table, but I've also seen stuff like this. So maybe it looks like this. So your x column won't start at 0, it might start at some other value, and then your x's look something like this. So sometimes students look at this and they're like, wow, my table starts at 0. Well, yes, the y value is 0, but the x value matching up to that is not 0. Remember, if something is going to be considered a direct variation, you need to have the exact point of 0, 0. So not only does the y value have to be 0, but the x value that goes with that also has to be 0. 0, 0 is the point that is representative of the origin. But for a partial variation, okay, you have to look for your initial value as the y value that shows up when x is equal to 0. So if I were to give you this particular table and I asked you to identify the initial value, you first need to scan your x column, look for the 0, and then the initial value is the value matching up to that in the y column. So the initial value here would be 5. If we're looking at a graph for a partial variation, it will cross the y-axis at an initial value that is not 0. So that's just a fancy way of saying your graph is not going to start or cut through the origin. So you could have a line that maybe starts over here and then grows or goes in an upwards fashion, or you might have a line that starts somewhere up here and then maybe goes in a downwards direction. So either way, neither of these lines start or touch or cross the origin. If you are looking to build an equation for a partial variation, well then the equation will take on the template y equals mx plus b. And this b value is representing the initial value. And since the graph does not have an initial value of 0 because it's not starting at the origin, you are going to have a value that needs to be inputted into the equation. So you could have a lot of different examples here. You could have something like y equals 2x plus 4. You could have y equals 5x minus 6. It is totally possible for your initial value to be a negative number. So for example, if I go back to my graph here and I erase these lines that I created, you could have a graph that starts below, and maybe it starts down here. Let's say this is a value of -1 on the y-axis. It is totally possible for your line to start at a negative number and then increase from there. If your line starts at a negative number, well then your corresponding initial value is obviously going to be a negative number. So it is possible to have a minus in your equation. So the key takeaway here is that direct variations are going to go through the origin or start at the origin, and so you will see 0, 0 as a point on your graph or as a point in your data table, and the equation will not have an initial value. For a partial variation, your graph is going to start at a value other than 0, and so your graph will not be at the origin as a starting point, and your equation will take on the form y equals mx plus b, where b represents your initial value.